Welcome to STEM Made Simple. This series is for researchers and engineers with a background in quantum physics who want to develop a working understanding of quantum computing. In this first episode, we'll address a fundamental question. What is quantum computing? Not from a popular science viewpoint, but from the standpoint of physical information processing governed by quantum mechanics. To begin, recall that computation is not an abstract process independent of physical law. Rather, it is a physical transformation of information. The classical model of computation, as formalized by the Turing machine, assumes that logic gates manipulate bits through deterministic or probabilistic processes consistent with classical mechanics. Quantum computing shifts this paradigm by recognizing that the laws of quantum mechanics can be used to define entirely new models of computation. The mathematical setting of quantum computing is the Hilbert space. A qubit is a unit vector in a two-dimensional complex Hilbert space, and its general pure state can be written as ket psi equals alpha ket 0 plus beta ket 1, with alpha and beta in the set of complex numbers, and the squared modulus of alpha plus the squared modulus of beta equals 1. This constraint preserves normalization under unitary evolution. Whereas a classical bit is confined to the values 0 or 1, a qubit can be in a continuum of complex valued superpositions. For 2 qubits, the state space is complex 4-dimensional space. For n qubits, it becomes complex 2 to the n dimensional space. This exponential scaling is a source of computational power, but it also presents challenges for control, storage, and error correction. Quantum operations are implemented as unitary matrices. For example, the Hadamard gate acts on the computational basis as h applied to ket 0 equals 1 over the square root of 2 times ket 0 plus ket 1. H applied to ket 1 equals 1 over the square root of 2 times ket 0 minus ket 1. The Pauli X gate performs a bit flip. X applied to ket 0 gives ket 1. X applied to ket 1 gives ket 0. This is analogous to the classical NOT operation, but now embedded in the algebra of operators over Hilbert space. Entanglement arises naturally in multi-qubit systems. The Bell state, ket phi plus equals 1 over the square root of 2 times ket 0 plus ket 1 cannot be decomposed as a tensor product of single qubit states. The non-factorizability implies correlations that have no classical counterpart and forms the basis for quantum protocols, such as teleportation and superdense coding. The process of measurement is modeled by projection onto an orthonormal basis. When measuring a qubit in the standard basis, the outcome is 0 with probability equal to the modulus of alpha squared, and 1 with probability equal to the modulus of beta squared. Measurement collapses the state, introducing an inherent stochastic element not found in classical deterministic systems. A quantum computer in its most common form operates through the circuit model. Computation begins in an initialized state, such as an n-qubit register in the all-zero state, which is also known as the ket-zero tensor product to the n. And this state evolves via a sequence of unitary operations and concludes with a projective measurement. These unitary operations must be reversible due to the unitarity constraint, and they often act non-trivially on entangled states. Quantum superposition does not permit arbitrary extraction of information from all branches simultaneously. The power of quantum algorithms lies in their ability to manipulate amplitude so that the undesired outcomes interfere destructively and desired outcomes interfere constructively. This principle is key to understanding quantum speedups. For example, in Grover's algorithm, a quantum amplitude amplification process increases the probability of measuring a target solution in an unstructured database search. The query complexity scales as big O of the square root of n instead of big O of n, which is a quadratic speedup. In Shor's algorithm, the quantum Fourier transform enables efficient period finding, leading to a polynomial time factoring algorithm. The underlying mechanism is the use of entanglement and an interference. Quantum computation also imposes new physical limitations, the no-cloning theorem, proven from the linearity of quantum mechanics, forbids the duplication of arbitrary quantum states. Moreover, decoherence and environmental noise pose serious challenges. Quantum error correction, which we will explore later in the series, provides a path forward by encoding logical qubits into entangled states of multiple physical qubits. These codes rely on the ability to detect and correct certain classes of errors without violating the uncertainty principle. From a broader perspective, quantum computing is not a single technology or architecture. It includes several distinct models, including measurement-based computation, topological quantum computing, and adiabatic evolution. Each of these models emphasizes different physical and mathematical principles, but they are all computationally equivalent in terms of the class of problems they can solve, given sufficient resources. For physicists, the appeal of quantum computing is not just its technological promise, but the way it reframes computation as a quantum process. Instead of calculating probabilities from a Hamiltonian, one now constructs controlled unitary evolutions to carry out transformations on information-bearing quantum states. In this sense, quantum computing represents a shift in role from observer of quantum systems to designer of quantum processes. Thank you for watching. In the next episode, we will examine the mathematical structure of quantum circuits and the behavior of quantum gates in detail. If this introduction has helped clarify the computational perspective on quantum mechanics, please like the video and subscribe to STEM Made Simple. Your engagement helps support the creation of rigorous, accessible content for professionals like you.